Welcome to the last section of this course, Support Vector Machines. In this section, we will start with classifying data with a linear SVM, then optimizing an SVM. Next, we will look at the multi-class classification with SVM, and finally explore support vector regression. Now let's move on to the video, classifying data with a linear SVM. In this video, we will start with loading the data, then use a NumPy mask to focus on the first two classes, and finally visualize the two classes. The main idea behind linear SVMs is to separate two classes with the best possible plane. Let's linearly separate two classes with an SVM. Let us start by loading and visualizing the iris dataset available in scikit-learn. First, we will import some libraries. This will then be used for visualization. Then we will load the datasets. This will load the first two features of the iris data, and this will load the target of the iris data. Now, we will use a NumPy mask to focus on the first two classes. In this, we will select only the first two classes for both the feature set and target set. The first two classes of the iris dataset are Setosa with 0 and versicolor as 1. Next, we will visualize the two classes. Plot the classes 0 and 1 with matplotlib. Here, x_0 refers to the subset of inputs x that correspond to the target y being 0, and x_1 is a subset with a matching target value of 1. Next, to visualize within IPython, we need to use these commands. Run the code and you would get the output as shown here. From the graph, it is clear that we could find a straight line to separate these two classes. The process of finding the SVM line is straightforward. It's the same process as with any scikit-learn supervised learning estimator. First, create training and testing sets. This will split the dataset of the first two features of the first two classes. With this, it will stratify the target set. Next, create an SVM model instance. Set the kernel to be linear, as we want a line to separate the two classes that are involved in this example. Then fit the model or train the model. After that, we will predict using the test set. Post that, measure the performance of the SVM on the test set. Run it and you should get the output as 1. It did perfectly on the test set. This is not surprising because when we visualized each class, they were easy to visually separate. Let's visualize the decision boundary, the line separating the classes, by using the estimator on a two-dimensional grid. For that, first import product from itertools. Then, with the help of these commands, we will get the minima and maxima of both features. Then, with this command, we will get grid or Cartesian product with itertools.product. Finally, we will get the predictions on the grid with this command. Once we are done with it, we plot the grid by coloring the predictions. Next, we will visualize the content with the help of these commands. Note that we have amended the earlier visualization to include SVM predictions. It's time to run it. Cool, we fleshed out the SVM linear decision boundary by predicting on a two-dimensional grid. As we know, the intercepts are contained in the SVM instance's intercept data attribute. We will view these two attributes. First, check with SVM instance.coefficient, and here you got the output array. Then we will check for the SVM instance.intercept, and after running we will get the output as highlighted. Additionally, you can view the parameters of the instance to learn more about it. Type in these commands for it. Run it and you would get the output as highlighted here. A final note on SVMs is that we could rescale the data and test that scaling with cross-validation. Conveniently, the iris dataset has units of CMS for all of the inputs, so rescaling is not necessary. But for an arbitrary dataset, you should look into it. So here we have come to the end of this video.